Hello, greetings. So after some conversations with some of your classmates, I just wanted to take a moment to record a video, just kind of going over um, what I want to say. So I want to talk about expanding fugacity, right? So throughout this course, we've expanded fugacity in terms of computing fugacity in different ways, and so I just want to kind of go through and try and make clear all the connections and how essentially we're just doing the same trick over and over again. Okay, and so what I mean by that, right? When I talk about expanding, right, I'm going to work in terms of logs here, just because it's easier to illustrate. Okay, but in general, the trick is if I want to compute the log fugacity of say component I, okay, well, I do my favorite mathematical trick of adding 0. Okay, and so on the right hand side, I'm going to write this as log fi plus, okay, I'm going to add 0 to my equation, and I'm going to add 0 in the form of the log fugacity of component I in some reference state minus the log fugacity of component I in some reference state. Okay, so log fi ref minus log fi ref, right, that's 0. Okay, and so I'm going to rearrange it, okay, so that it takes the form of log fi ref, okay, plus log fi minus, and actually I'm going to take it back. I want to switch the order. I'm going to write as log fi minus log fi ref, okay, plus log fi ref. Okay. So I'm going to write log fi as, right, this term log fi minus log fi ref plus log fi ref. So in general, our goal is if I'm trying to compute the fugacity of component I, is I want to choose a reference state, right, that's as close to my system as possible, right? Because on the right hand side, essentially what I have is this is like a perturbation expression, right? So I'm trying to calculate the fugacity of component I as being equal to that of some reference state value plus a deviation term. I want to choose my reference state, right, as close to my system of interest or my state of interest, so that my deviation term is as small as possible, so I can compute it as accurately as possible, or this is what's going to lead to allow us to make some suitable assumptions in terms of solving problems. So I want this to be as small as possible in terms of accuracy of calculation standpoint, but then from the ability to make assumptions standpoint. Okay, and so I want to choose a reference state as close to my system as interest. Okay, cool. So the first kind of reference state we talked about is thinking about ideal gases. Okay, so choosing an ideal gas reference state. And so choosing an ideal gas reference state, this works really well when modeling vapor phases, right? So I'll just make a note, right? Choosing an ideal gas reference state works really well when modeling vapor phases, right? Why? Because a vapor phase, right, adopting a reference state of an ideal gas to model a vapor phase, well, they're going to be reasonably close, right? In the vapor phase, the molecules are pretty far apart, so their interactions are usually pretty small. So adopting a reference state as an ideal gas where those molecules aren't interacting, right, is a good choice. Okay. What I should add is, right, besides choosing a reference state as close to my state of interest, is I also want to choose a reference state for which I can compute. I have analytic expressions in which I could actually compute the fugacity of said reference state. Right. So this is something I want to be able to readily compute. Okay. So the first reference state we looked at was the case of an ideal gas, which is a useful reference state when modeling vapor phases. Okay, and so in that case, okay, I'm just going to make a note, right? Ref is equal to ideal gas. So when I write this out, I end up with the log fugacity of component I is equal to, okay, my deviation term log fugacity of I minus log fugacity of I. Now my reference state is that of an ideal gas. Okay, plus log Fi ideal gas. Okay. Now this first term, log Fi minus log Fi ideal gas, well, that's just equal to log phi. Okay, and just to make a completeness, okay, this would be 1 over RT Gibbs free energy or partial molar Gibbs free energy component I minus partial molar Gibbs free energy component I in an ideal gas state at the same conditions. Okay, so log phi is equal to 1 over RT times my partial molar residual Gibbs free energy component I, okay, just for completeness. And fugacity of component I in an ideal gas state, well, that's just equal to its partial pressure. So if I'm thinking about vapor phases, right, I'll write my mole frac is Yi, right, but it's partial pressure Yi times P, right, or partial pressure. Okay, cool. Okay, so this is in terms of logs, right, not in terms of logs, right. It takes the form of Fi is equal to phi times the fugacity of an ideal gas, which is yi times p. Okay, but the general premise is I'm taking my fugacity and I'm computing it as some reference state value plus a deviation term. Okay, I want to choose my reference state value as close to my state of interest so that my deviation term is as small as possible. And I also want to choose this reference state so that I can analytically, so I have ways to analytically compute its value. Okay, and then in choosing a reference state as close to my state of interest as possible, well then it's going to allow me to more accurately compute my deviation term, right, in the form of a perturbation theory. But then this is going to set us up to be able to make suitable assumptions, right? And so if I have a vapor phase at low pressures, right, so that I can assume that it's an ideal gas, well, then phi is just going to become 1, right, and all is good. Okay, so this deviation term, right, is going to become 0, right, in the limit that I have that reference state value. Okay, cool. So in this case, in the ideal gas limit, or if I can assume I have an ideal gas, phi is just 1. Okay, all right, cool. Now, before we get into chapter 12 and talking about modeling deviations from ideality in liquid phases, okay, I'm going to first need to talk about where Poynting correction came from, right? Because Poynting correction came from the same exact place. Okay, so next I'm going to talk about our friend Poynting, okay, and what Poynting actually is. Poynting, right, and reminding us of the origin. Okay, so when I'm talking about Poynting correction, okay, what I'm trying to do is I'm trying to calculate the fugacity of a pure component state at a given temperature and pressure, okay, where typically we have that my pressure P is greater than the corresponding saturation pressure at that T. So typically I'm modeling a compressed phase, say a compressed liquid. So where Poynting correction comes in is I'm trying to calculate the fugacity of a pure component state at a given temperature and pressure, where my pressure is greater than the corresponding saturation pressure at T. Okay. All right, so I'm going to do the same exact trick, only what I'm going to do is I'm going to rearrange this equation here. Okay, so my goal is I'm going to calculate the fugacity of component I, okay, at some given temperature and pressure. Okay, and how I'm going to do that is I'm going to write my expansion. I'm going to, well, I guess I don't need to flip it, well, okay, I don't need to. I'm going to flip it because that's how we did it in class. So I'm going to write it as log fugacity of component I, okay, I'm going to write it as a reference state for now, plus log Fi, okay, at T and P, minus log Fi ref. Okay, so all I did is flip the order, because that's how we did it in class. So in the case of Poynting, what I'm going to do is I'm going to adopt as my reference state pure component at saturation. Okay, so where Poynting came in is I'm trying to calculate the fugacity of component I at a pure component I at a given temperature and pressure. Okay, where my pressure is greater than the corresponding saturation pressure, right? So I'm dealing with, say, a compressed phase. So in the context of calculating the fugacity of my pure component system at a given T and P, I'm going to adopt as a reference state my pure component at saturation at that T. Right, so my reference state, right, is going to correspond to that pure component in a saturated state at that T. Okay, so what I end up with is log fugacity of I at T and P, that's pure component I, is equal to the log fugacity of component I at saturation, okay, and that's at the same T, right, at T, plus, okay, now I have my deviation term, which I'm going to write as log Fi at T and P minus log Fi sat at T. Right? T, technically it's at a pressure equal to its saturation pressure. Okay, cool. So now I take this term by terms. Okay, in terms of choosing my reference state, all right, I choose my reference state so that it's as close to my actual state as possible, so that my deviation term is as small as possible. But then we also want to be able to, compute, right, say this, reference state value. All right, so now in terms of fugacity here, this is the fugacity of component I at a given temperature and pressure. This is the fugacity of pure component I at saturation at that temperature. So this is pure component I at saturation at that T. If I have pure component I at saturation, so vapor-liquid equilibrium at that T, the fugacity of the liquid and the fugacity of the vapor are the same. Okay, so if I need to calculate the fugacity of component I at saturation, I could compute the fugacity of the vapor or the liquid. Either one, all would be the same. Okay, so I'm going to look at it from the perspective of the liquid, right? And so we just talked about I'm going to look at it from the perspective of the vapor, and we just talked about calculating fugacities of vapor phases, right, in our previous kind of example. And so what I'll have is that if I were to calculate the fugacity of component I at saturation, right, at T, okay, well, that's just going to be equal to the fugacity coefficient of component I at saturation at T times, well, I don't need a mole frac because it's pure component I, so it's just a pure component system. So phi sat times pi sat. Okay, and this is great. So if I'm at for my saturation pressure, so if I'm at a low pressure, so I can assume the vapor phase is an ideal gas, well, then the fugacity coefficient would just be 1. Okay, and pi sat, well, that's something I could readily compute via an Antoine equation. I could look it up if I have tabulated data, say the steam tables, or I could compute it using an equation of state. Right, so pi sat is something I can readily compute or find. And if I'm at low pressures, so that I can assume I have an ideal gas, well, that's just going to be equal to 1. Right, so vi sat or fi sat, I can just compute as vi sat times pi sat. And then in terms of this deviation term, the deviation term, right, that's my Poynting correction. Okay, so Poynting is the deviation term. So Poynting is the deviation term. Okay, so Poynting's the deviation term, just as phi was our deviation term, right, when we were thinking about computing fugacity relative to an ideal gas reference state. Okay, so Poynting's the deviation term. How we computed that, right, the key was remembering that difference in log fugacities. So this would be log fi relative to log fi sat. That's equivalent to 1 over RT times, so Gibbs free energy at my state of interest minus my Gibbs free energy at saturation. Okay, so if I want to compute that difference, okay, key was I'm at the same temperature, so the differential of now I need to try and remember it. So the differential of G over RT. Okay, so if I were to integrate that, I'd get a difference in G's. So I believe it's negative H over RT squared dt plus V over RT dP. Okay, but if these two states are at the same temperature, okay, right, dt is equal to 0, and so I just have that the differential of G over RT is equal to V over RT dP. Okay, cool. So how I get my Poynting correction then is log fi relative to log fi, or log fi minus log fi sat. So log fi relative to fi sat would be the integral of the differential of G over RT. Okay, and I'm going to integrate that. I'll write it as from pi sat, pressure equal to the saturation pressure, my pure component I, to my pressure of interest, and that's going to be equal then to the integral of V over RT dP, okay, from pi sat to P. Now the common way we represented this, open a new page, the common way that we looked at this, or the common expression we see, is, well, in order to evaluate this integral, I need to know how V changes with respect to P. And so the common situation is, well, we're already looking at, say, a compressed liquid, right, a phase where my pressure is greater than Psat. So if we assume that it's incompressible, well, then that just means that my volume is insensitive to pressure, so I can bring it out, it's constant. So if it's incompressible, which is the common form we see, that's where we ended up with log fi over fi sat, okay, is equal to V over RT times P minus pi sat. Okay, and that's nothing more than our Poynting correction. Okay, it's just a matter of oftentimes we didn't write in terms of logs, so it'd be the exponential of this term. Okay, so this is my Poynting correction. Where we typically end up seeing it is not in terms of logs. Okay, but if I were just to expand fugacity component I at a given temperature and pressure, okay, and I should say, right, this is equivalent to, I could write this as fugacity of component I, relative fugacity of component I at saturation, right? Or actually, let me write it as fugacity of component I at saturation times, I flip the order this time, fugacity component I relative fugacity component I at saturation. Okay, so if I were to expand, I get the fugacity component I to given temperature and pressure, right? It's phi sat. Okay, and I'm going to put my functional dependencies in there at T times pi sat, okay, at T, and then my Poynting correction, okay, which would be the exponential of, I don't have enough room, so I'm going to write times my Poynting correction, which would be the exponential of, this is it for an incompressible fluid. Okay, if I had to worry about change in V, I'd plug in that, but just to keep it simple, V over RT, P minus P sat. Okay, but the key is, right, we're doing the same trick. Right, I'm trying to calculate my fugacity to given temperature and pressure, and so I'm writing it as, in this case, a reference state value plus a deviation term. Okay, the reference state value, key here, is at pure component saturation, the fugacity of my liquid and vapor would be the same. So if I think of the fugacity of the vapor phase, that's just phi sat times pi sat. We just talked about computing fugacities of vapor. And my deviation term, right, that's my Poynting correction. Okay, and then we do similar tricks. So if I'm at low pressure is well removed from my critical point, right? And so what I mean by that, so if I'm at low pressures or low temperatures, P, if P is around 1 bar, P sat's going to be, say, less than 1 bar. This term typically becomes pretty negligible, right? And so then if I'm a ideal gas, right, then that, or if I can assume that the pure component at saturation T can be treated as an ideal gas, right, that becomes 1, and a first order approximation, my fugacity is just equal to my saturation pressure, right? Cool stuff. All right. Then the next case we had, comes in chapter 12, is, okay, so here, right, we're adopting a reference state of an ideal gas, which is good for modeling vapor phases. Now, if I'm trying to model a liquid phase, an ideal gas isn't a good reference state. Why? Because the reason I have liquid phases, the reason I have condensed phases, is because molecules are interacting. So adopting a reference state in which molecules aren't interacting, right, well, our actual system's going to be pretty far from that idealized limit. Right? And so when we model liquid phases, we'll typically expand with respect to an ideal solution. Okay, so we'll typically adopt an ideal solution, right, and this is going to be for modeling liquid phases. Okay, now we'll talk about Henry's next, right? So we do need to be careful when we talk about ideal solutions. So ideal solutions here, sometimes they're referred to as ideal solutions in the Lewis-Raoult sense of things, or ideal solutions in the Raoult's law context. Okay, but the key is, ideal solution. The ideal solution we've talked about in class, in chapter 12, is this case in which we have a system in which all the intermolecular interactions are exactly the same. So the molecules interact, but they're all exactly the same. Okay, and so and so all solutions are going to approach ideal solution behavior in the pure component limit. Right, a pure component solution is an ideal solution, in a pure component solution, all of the interactions are exactly the same. Okay, so when we adopt Raoult's law standard state to model a compound, typically we're talking about liquid phases like a mixture of methanol and water, where the two components could span the entire composition region. Okay. All right, so when I talk about an ideal solution in the context of chapter 12, well, so my fugacity of component I, okay, it's equal to my deviation term, log fugacity of component I, minus the log fugacity of component I, an ideal solution, plus my reference state, log fugacity of I, and an ideal solution. Okay, cool. Log Fi minus log Fi ideal. Okay, our deviation term when we're dealing with modeling our liquid phases, so deviations from ideal solution behavior, that's going to take the form of log gamma I. Gamma I is the activity coefficient. Okay, and sometimes you'll hear activity coefficient in the Lewis-Raoult sense or Raoult's law sense. It's just that's being clear exactly how we're defining an ideal solution, because it could be defined in a number of ways. Okay, but in our class, right, that's an ideal solution. So that's log gamma I, right, and then for completeness, okay, this is log Fi minus log Fi ideal. That'd be 1 over RT, partial molar Gibbs free energy component I minus partial molar Gibbs free energy component I in an ideal solution. So that's my partial molar excess Gibbs free energy of component I. Cool. Now, fugacity of component I in an ideal solution. Okay, well, fugacity of component I in an ideal solution. Okay, for an ideal solution, that's mole fraction xi times Fi pure. Okay, well, how do I get xi pure? Okay, well, xi pure, or Fi pure. Fi pure, well, that's just this, right? If I want to calculate the fugacity at a given temperature and pressure, right, I can use the expression that we just worked out using our Poynting correction. Okay, cool. All right, and so, for completeness, if I want to calculate Fi pure, so the fugacity of pure component I at a given temperature and pressure, okay, just to write it out without our functional dependencies, since we just had it, it'd be phi sat times pi sat, pure component system at vapor liquid coexistence, times, okay, my Poynting correction, where if it's an incompressible fluid, that's V over RT, P minus P sat. Okay, cool, right? And we do similar tricks, right? So, if I'm thinking about when we with derived Raoult's law, right? Oh, so just to expand it out, just for completeness. So then putting it all together, we'd have Fi is equal to gamma I times Xi times Fi pure, which is this, times phi sat times pi sat, right, times Poynting. Okay. So we choose our reference state to be as close to our state of interest as possible, so the deviation term is as small as possible. That's going to give us, confidence in our ability to accurately compute the deviation term, but then also setting us up to make reasonable assumptions. So when I look at our expansion here, right, we can go through things in order, right? If we're at low pressures, well removed from the critical point of either component, right, typically we can assume the Poynting correction is negligible. Okay, if I can assume that my vapor phase is an ideal gas, so if I'm at again low pressures, and so this is pure component I at saturation at that T, so pressure would probably even be lower than say 1 bar. May even be lower than 1 bar. So if I can assume it's an ideal gas, right, that's just equal to 1. And then if I assume I have chemically similar compounds, gamma I is equal to 1. Right? But if I don't have chemically similar compounds, well, then I've got that deviation term I need to compute. Right? So it allows me to systematically go through and simplify my equation for making actual calculations. Okay. And the other thing I'm going to point out is if I go up to our ideal gas case, now that we have it, okay, that we use to model vapor phases, then our ideal solution case, right, another big motivation for using fugacity instead of say chemical potential, right, and say expanding our fugacity when we solve problems, right, is these are now explicit in composition, right? So on the right hand side, fugacity is a function of temperature, pressure, and composition. But now on the right hand side, I explicitly have composition. Okay. Now gamma I is a function of temperature, pressure, and composition as well. Okay, but I have xi, which is a function of composition. All right, just like I have yi over here, right, when I expanded, say, the fugacity of my vapor. So I end up with expressions which are explicit in my quantity of interest, right? When I'm designing the distillation column, what I'm interested in is I'm interested in the composition of my, bottoms and distillate product. Okay, and so now I end up with expressions which are explicit in those quantities that I actually want. Okay. All right, so the next thing I'm going to do is in chapter 13, we talk about Henry's law. Okay, so now the idea here is in chapter 11, right, and then here's looking at deviations from it, we define an ideal solution. An ideal solution is one in which all intermolecular interactions are exactly the same. Okay, a solution in which all of our interactions are exactly the same. All solutions approach ideal solution in the pure component limit. Okay, so where we typically model a compound in solution using this reference state is if I'm modeling, say, vapor-liquid coexistence of water and methanol, where water and methanol I expect to span the entire composition region. Okay, what we're going to talk about next is we're going to talk about ideal solution, but in the Henry's law context. So I'm going to call it, ID, right, dash H. Okay, and this kind of came up when we were deriving our expressions for relative humidity, which we can do momentarily. But the idea behind chapter 13, and then this new ideal reference state, is so when we were talking about relative humidity, we were looking at things like equilibrium between water and air, right? So equilibrium between water and a non-condensable component. Okay, what we meant by non-condensable is if I think about, say, oxygen and nitrogen as making up air, right? Both of those components are going to have critical temperatures greater than, say, our temperature, or less than our temperatures of interest. So I can't remember exactly, but I think nitrogen had a critical temperature on the order of, say, 150 Kelvin. And so if I'm looking at an equilibrium between water and air, or water and nitrogen at 298 Kelvin, 25 degrees C, I'm at a temperature greater than the critical temperature of nitrogen. So my temperature is greater than the critical temperature of that component. But if I'm at 1 bar, say, our pressure would be less than the critical pressure of nitrogen. So if I were to look at a PV phase diagram, that's going to put us squarely in the superheated vapor region. All right, and so, by non-condensable component is if I'm at 25 degrees C and 1 bar, right, under those conditions, they're not going to be able to, say, condense that component, right, that compound, right? It's squarely in the superheated vapor region. All right, so when we talked about this equilibrium between, say, water and air, or water and a non-condensable component, okay, we assumed that we could assume the liquid phase was essentially pure water because the solubility, right, or the mole frac of that non-condensable component in the liquid phase is going to be really, 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 really small, right? The amount of nitrogen or oxygen, say, in water is going to be really, 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 really small. So if I think about the last ideal, kind of reference state, right? So here we talked about ideal solutions in terms of modeling liquids, okay? So if I think about gamma I here, okay, well, gamma I, okay, so if I look at the limit of gamma I as, say, xi goes to 1, right? So key is all solutions approach ideal solution in the pure component limit. So in the limit that I have a pure component system, right, gamma I is just going to be equal to 1. Okay? And so when I talk about, kind of this deviation term, okay, we're looking at, two components that are going to be able to span the entire composition region, right, say from 0 to 1. I'm modeling vapor-liquid equilibrium between water and methanol. If I'm thinking about the relative humidity case, okay, the difference is that I'm going to have a non-condensable component in solution, and it's going to have a really, really small concentration, right? Under no conditions am I going to be able to get, say, a mole fraction of that component anywhere close to 1, right, in the liquid phase. Okay. And so that's going to lead us to adopt a new idealized state, right? We're going to adopt a new reference state or a new idealized state. Okay. So here we're going to adopt a reference state, okay, or an idealized state, and we're going to call it it's going to be an ideal solution, but this is where we call it an ideal solution in the Henry's law context. So an ideal solution in the Raoult's law or Lewis-Randolph's case, right, that ideal solution, we're assuming we have intermolecular interactions, but they're all exactly the same. And, gamma I, that deviation term, right, it's going to go to 1 in the pure component limit. Okay. Well, what we're going to assume is an idealized state in the Henry's law context is we're going to assume we're going to take a reference state or an idealized state to be the case where my compound of interest is infinitely dilute in solution. Okay. So what do I mean by infinitely dilute? I have, say, 1 molecule of nitrogen and some infinite number of water molecules, right? This idea that in this system, all I'm going to have present are going to be water-water, so solvent-solvent, and then solute-solvent interactions, right? There's going to be just one solute in solution, so the solute is only going to be interacting with water. There's no other solutes to interact with, so there's no solute-solute interactions. Okay, so now, conceptually, my idealized state is this case in which I have a solute infinitely dilute in solution. Okay, so I have one solute molecule and then all solvents. So there's solvents interacting with solvents, and then there's solvents interacting with solute, but there are no solute-solute interactions. Okay, cool. So then the idea is even if I'm at small concentrations, okay, in general, the concentration is going to be small enough that those solute molecules aren't going to see any of their solute molecules, right? So, right, we're only going to have small deviations from this, idealized reference state. Okay. So when I write out my log fugacity of, say, component I in this case, okay, it's going to be equal to, so now my deviation term is going to be log fi minus log fi. I'm going to put a superscript h in terms of the fugacity of this idealized state, okay, plus log fugacity, right, of this ideal state in the Henry's law context. Okay. So this term here, right, is going to take on, right, it's going to get the name of log and gamma I, but now I'm going to put a superscript h on here because this is an activity coefficient defined in the Henry's law context. Okay. And then FIH, okay, the fugacity of component I in a Henry's law context is going to take the form as mole fraction Ki times KIH. So now KIH is my Henry's law constant. Now KIH, okay, what's going to be important is this is unique to the solute and solvent. Okay. And again, what we're trying to do here is concentration of gases in solution is going to be really, really small. So we're going to take our reference state to be a solute infinitely dilute in solution. So if I have a solute infinitely dilute in solution, that's a one solute molecule and an infinite number of solvents. So conceptually, in that system, I have solvent-solvent interactions and then solute-solvent interactions. There are no solute-solute interactions. Okay, cool. Okay, so even if I have a small number of solutes in solution, right, the idea is that those are all completely solvated by other solvents. So the solutes don't see each other, right? Their interactions are virtually zero, right? So even at small concentrations, that deviation term is pretty small. Okay, the deviation term would come into account if I start to have larger concentrations, where now I need to begin to count for solute-solute interactions in solution. Okay. Cool, right? And this is Henry's law, right? This is Henry's law. I mean, so this is a little different. Because now it's fugacity of component I relative to fugacity of component I in a Henry's law context, right, which would be an infinitely dilute solute. So you don't get something cute like residual or excess, right? You'd get 1 over RT partial molar Gibbs free energy minus partial molar Gibbs free energy of an infinitely dilute solute, right? So this would be 1 over RT gamma I minus gamma I at infinite dilution, right? Infinity is the symbol that we typically, use to designate a compound that's infinitely dilute, right? And what I would mean by infinitely dilute is, mathematically, that's the limit that the mole fraction goes to 0, right? Of say GI, right? That's G bar I, infinite dilute, right? So the limit that its mole frac goes to 0. Okay, so that's the premise behind Henry's law. Okay. That's the premise behind defining ideal solutions in the context of chapter 11 and 12. And then here's our Poynting. Here's our expansion in terms of modeling vapors, right? And if you want to keep watching, right? If we put it all together, right? We can, right? So if I start with so Henry's, if I would expand it, fugacity of component I is gamma H times Xi times KIH. So let's start simple, right? So since we just talked about Henry's, let's just look at, say, solubility. So actually, let me do solubility of gases and liquids, but let's just do like VLE, right, with a non-condensable component. All right, so if I have non-condensable component, okay, component, okay, so let's say component 1 is water, and let's let component 2 be, say air, and I'm just going to call it, nitrogen. Okay, cool. All right, so if I first think about component 1, right, this is what we talked about in terms of relative humidity. So if I'm looking at vapor-liquid equilibrium between water and a non-condensable component, okay, well, let me start with component 1. So the fugacity of component 1 in the vapor is going to be equal to the fugacity of component 1 in the liquid. I then expand. So in the vapor phase, it's going to be phi1v times y1 times p. In the liquid phase, it's going to be gamma 1 times x1 times phi1 sat times p1 sat times my Poynting correction. So let's assume though now maybe we're at say 25 degrees C, right, in 1 bar. Okay, we're at 25 degrees C in 1 bar. Okay, well, one, we're going to be at low pressures. Okay, so it's going to be reasonable to assume vapor phase is an ideal gas. Right? So assume the vapor phase is an ideal gas. Now this would be pure component at saturation at 25 degrees C. Pure water at vapor liquid coexistence at 25 degrees C. Well, that's going to be at a pressure even less than 1 bar. Right? 1 bar is the saturation pressure at 100 degrees C. Okay, so if I'm assuming that my vapor phase is an ideal gas at 1 bar, right? If I'm even lower, sure. Okay, cool. Now, if I'm at low pressures, right, Poynting correction is also going to be reasonable to assume that it's 0. So this would be 1 minus some number less than 1. Okay, so this term in brackets, right, it's typically going to be 0. So the exponential of 0 is just 1. Okay. All right, now let's think about this in terms of water, right? The mole frac, or how much nitrogen is going to be dissolved in water, right? The mole frac of nitrogen in water is going to be really, 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 really small. Okay, so if the mole frac of water or nitrogen is really small, the mole frac of water is going to be really, really close to 1. Okay, so if x1's close to 1, right? When we talked about relative humidity, we just went as far as to assume that x1 was equal to 1, right? Cool. And then if x1 is approximately equal to 1, well, then it's going to be reasonable to assume that gamma, right, is close to 1, because in the limit that x1 goes to 1, gamma 1 goes to 1. So when we talked about relative humidity, our governing equation just became y1p is equal to p1 sat. Okay, cool. So by being able to write my isofugacity equation and expand, and I got my relative humidity equation. Okay, great. Now we assume that x1 was 1. It's all right, but if we didn't assume x1 was 1, right, we'd put an x1 in here. Okay. Now let's think about component 2, right? So now we're going to think of this in terms of gas solubilities. Okay, and so as I talk about solubility of gas or solubility of nitrogen, again, right? Rigorously, I could say this is then say x1 times p1 sat, where we expect x1 to be close to 1. Okay, so in terms of gas solubilities, right, it's the same trick now for component 2. We say, okay, if I'm nitrogen, the fugacity of nitrogen in the vapor is equal to the fugacity of nitrogen in the liquid. In terms of the vapor phase, I'm going to have phi2v times y2 times p. Now in terms of the liquid, okay, I expect the solubility of nitrogen, or the mole frac of nitrogen in the liquid phase, to be really, really small. So the reference state I'm going to adopt is going to be a Henry's law reference state. So I'm going to adopt an ideal solution in the Henry's law context. So on the right hand side, I'm going to write gamma IH times XI times KIH, where KIH would be my Henry's law constant for nitrogen and water, right? It's important to, when we talked about, in chapter 10, so when I adopt an ideal solution reference state, right? This, fugacity of an ideal solution, okay? So as I expand it out here, fugacity of an ideal solution, mole fraction times fugacity of component I in a pure component state, right? This is, it's a pure component property. It's mole fraction times a pure component property, right? A property just of component I. Okay. Here, when we expand with the Henry's law standard state, okay, KIH is a property of the solute and solvent, right? It's meant to, account for, say, a solute infinitely dilute in solution. So this is a property of the solute and a solution. Okay. So in terms of gas solubilities, right, expand my fugacities, or write out my isofugacity equation, expand just as before. I do the same thing, right? If my pressure is low, so the vapor phase could be assumed in ideal gas, right? That's equal to 1. If I were to assume that the mole frac of component I in solution is relatively small, so that it's not going to deviate much from my reference state, right? Then I can assume gamma IH, right, is equal to 1. That's an ideal solution in the Henry's law context, right? Cool. So I end up with Y2P is equal to Xi times KIH. Okay, cool. Oh, and this is not Xi and Ki. I got to write down component 2, X2 and K2. Okay, cool. All right, so the first thing I'm going to do is an aside. Okay, is if I solve for X2, right, X2 is equal to Y2P over K2H. Okay, now K2H, right, said it's a property of the solute and solvent. It's going to be a function of temperature. Okay, and so without even talking about temperature dependence of my Henry's constant, just looking at this, right, if I have this equilibrium, so if I have air in equilibrium with water in a closed container, okay, so say it's a piston cylinder apparatus, right, as pressure increases, so if I put more weight on my piston head, so if the pressure increases in my column or my container, but say the mole frac in the vapor phase is constant, well, so as pressure increases, what that tells me is the gas solubility is going to increase, right? So as I increase the pressure, the amount of nitrogen in my liquid phase is going to increase, right? So this is, I have a can of soda, right? It's under pressure, right? It's under pressure because as I increase pressure, the solubility of those gases increases. I open my can of soda, the pressure decreases, okay? And so if I were to leave that on my counter long enough, right, it's going to go flat because the equilibrium solubility, right, of that gas at atmospheric pressure is going to be relatively small. Okay, it takes a little while for it to bubble, but that becomes a problem for Dr. Dewan. That's a mass transfer problem, so you can ask him about that in transport. Okay, but yeah, cool, right? And gases are interesting compared to solids. As temperature increases, gas solubility decreases. Okay, whereas with solids, we said as temperature increases, solubility increases. Okay, so what's going to happen is as temperature increases, my Henry's constant is going to increase, which causes X2 to go down. Okay, but we're not talking about temperature dependence here. Okay, but yeah, some cool stuff. And yeah, I'm trying to think of if there's anything else I want to say about that. And if you have our equation here for component 1, we have our equation here for component 2. Right, and so if you knew, say, pressure and Henry's constant, right, so if you knew pressure and Henry's constant, and then so if you knew your temperature, pressure, and Henry's constant, so temperature would give you P1 sat, right, you've got your two equations, you'd have your two constraint equations that your mole fractions need to sum to 1, in the vapor and liquid phase, right, you could solve for your Y1, Y2, X1, and X2. You could solve for your equilibrium values. Okay, cool. But yeah, and so that's kind of a new piece. If I'm modeling vapor-liquid coexistence, okay, and then I'll say I've talked for long enough. Okay, so if I'm talking about just vapor-liquid equilibrium in general, so say methanol and water, where the two components can expand the entire composition region. Okay, just writing it out in general. Right, I'd have the fugacity of component 1 in the vapor is equal to fugacity of component 1 in liquid. I expand my vapor, and so that's going to take V1V times Y1 times P, liquid, right, gamma 1, okay, times X1 times F1 pure, so V1 sat, okay, times P1 sat, times my Poynting correction, exponential, V over RT, P minus P sat. Okay. So cool, right? And so then it's a matter of systematically making assumptions. Okay, so if I'm at low pressures, and let's kind of talk about the assumptions. Okay, so in terms of hierarchy of terms appropriate to kill. Okay, so typically, I'm operating the distillation column near atmospheric pressure. Okay, so if I've got two components like water and methanol, all right, in a typical process, we're going to be at low temperatures and low pressures, right, well removed from the critical point of either of those components, so that my Poynting correction, right, is almost always going to be essentially 0. Okay. Well, the term in brackets is essentially going to be 0, so the exponential of 0 is 1. Right. So we almost always kill the Poynting correction. Where I have allowed my Poynting correction to live is if I'm modeling things like supercritical CO2. So like solubility in supercritical CO2, extreme pressures, hundreds of megapascals, right? Let's include that. Okay. Now, in terms of the remaining terms, okay, the next one in line that we typically kill is we typically assume the fugacity coefficient, right, of my vapor phase, and then that pure component at saturation is approximately 1. And so again, if I have something like water and methanol, and I'm operating a distillation column at around 1 bar, okay, it's typically reasonable to assume that that vapor phase could be treated as an ideal gas. Right? It's reasonable to assume that phi1V and phi1sat are approximately 1. Where we run into trouble is, one is, if the pressure increases. So if I'm at higher pressures, say 4 or 5 bars, right, you might start to think about accounting for non-ideality. But what we really need to worry about is if we have components that are known to associate. So a common one is acetic acid. And so in the vapor phase, if I have pure acetic acid is known to dimerize. Okay, and so if I have acetic acid dimerizing, well, then I've got acetic acid interactions. So I have interactions between those molecules in the vapor phase. Well, that's not an ideal gas, right? An ideal gas is a system in which molecules aren't interacting. So if they're associating, they're interacting, an ideal gas isn't a good reference state. So if I have components that are known to associate, right, then I would need to account for those. Okay, and I will add that if I'm using a process simulator, right, it isn't so bad to calculate these, because the process simulator could compute these using a cubic equation of state. Right? It's not us actually doing it, which is harder, I suppose. Okay, but kind of next in line is we typically assume that our vapor phase is an ideal gas. Okay, but this is where you need to be the intelligent user in your process simulator. And so if you're at higher pressures or your components, suspect that they might associate, you're gonna have to make sure you check that box in ChemCAD or Aspen to make sure you account for vapor phase non-idealities. Okay. And so if we just made those assumptions, we end up with y1p is equal to gamma 1 times x1 times p1sat. Okay. This gets the name. This equation is used a lot and gets the name of modified Raoult's law. Right, it's the modified Raoult's law. Why is it the modified Raoult's law? Well, because in Raoult's law, they additionally assume that the liquid phase is ideal, which means gamma is 1. So Raoult's law ends up with y1p is equal to x1, right, times p1sat. Okay. This is Raoult's law. So Raoult's law additionally assumes that the liquid phase is ideal. Okay. When is it reasonable to assume that my liquid phase is ideal? Well, if I have chemically similar compounds. So if I have a mixture of benzene and toluene, or a mixture of alkanes, then it might be reasonable to assume an ideal solution. Okay. But in general, right, that assumption, assuming an ideal solution, that's the worst of all of them, right, or the one that fails most often. Right. So yeah, Raoult's law, it would additionally assume solution phase is ideal. Modified Raoult's law throws our deviation term in there, right? It accounts for deviations from ideal solution behavior. And then in terms of these, killing the Poynting corrections, usually fairly common unless I'm at extreme pressures. And then these fugacity coefficients, just need to be conscious. So if I'm at higher pressures, I'm going to need to calculate those or account for those. But really, where I most need to worry about them is if I have components in the vapor phase that I'm assuming or are known to associate or interact with each other, where that ideal gas assumption would break down. And so this is where you just need to be an intelligent user, in that when I go to ChemCAD, right? So ChemCAD is what we use, here, but ChemCAD by default is going to, model vapor-liquid coexistence using a modified Raoult's law. Okay, but if you suspect that you're at higher pressures, that you're going to have some deviation from, that this ideal gas, approximation is going to break down because you're at higher pressures, or if you're dealing with, acetic acid or some components that are known to associate, well then, I'm going to have to account for these deviations here. Okay, and so you would check the box, right, to account for those deviations from ideality. Okay, And if you really want to use Raoult's law, right in the drop-down menu for excess Gibbs free energy models, they've got one for Raoult's law. Okay. But yeah, hopefully that's enough for me. This is a pretty long video, but hopefully you enjoy it. Look forward to seeing you in class today.